All righty, so it's probably streaming again. For those of you that just came in, these are the problems that after today's class, you're going to want to do them again, or some of them for the first time. And if you really do the practice, this graphing portion at least should be either you get it all, or if you didn't do the practice, you'll fail it all. So you definitely need to practice. That said, let's go to some screen share. And I'm probably going to do a bit more screen share than usual today because we're doing some graphs and they take a long time to draw on the board. Let me start with question, I think 2.27. So to be clear, let me mention a couple of things. 2.26 is up here. This graph goes with 2.27 down here. 2.26, if you're wondering what I'm talking about, you probably already know. That simulation was this one. So I'll put that simulation in the chat. If you guys want to play with this simulation, I can't remember if I've shown you. I recommend doing the Java. So that's that simulation. If you want to kind of get a visual representation of this and punch in some numbers and feel that out. And like I said, I would recommend going with the Java version down here. It just runs better. Okay. Let me get out of that and start over. So now let's go over here. Let's see. This first page, you're going to want to have this bookmarked for the meantime, page 31. All right, page 31 here. That's got all of our rules. And I can't stress this enough. I've seen so many students tank on these problems. Whoops. Geez, I keep hitting the wrong button. Sorry. I see so many students tank on, oh, geez. My gosh, I'm like loopy today or something, right? The most common thing students do on test day is they spend all this time learning these rules. And then when they get a VT graph, they'll use the XT rules or vice versa, and they'll screw up everything. So you need to know what type of graph you have before you start bothering to do anything. All right, so let's clear that, hit the right button this time. All right, and so we'll scroll down here to 227. And here we are. I'm going to scale this down to about 125. So we're going to spend some time working on this one. And before you think about it too much, I'm going to give you a short period of time to think about these first 4 bullets, okay? So I want you to think about the first 4 bullets. If you want, you could pick a random person and send them a private message and say, this is what I got, this is what you got. I'm not a huge fan of the Zoom breakout rooms. So, if you're super passionate about that, great. But to be honest, I really appreciate that you guys are not, students get freaked out about like, oh, I'm going to look so stupid. Number one, I can't even see you right now because I got too many windows. Number two, who cares about looking stupid? This is a physics class. No matter what you say, anybody out there in the real world is going to look at this and think you're a genius because you're taking a physics class, right? So you guys have not been bashful, and I really appreciate you guys speaking up. Okay, I'm going to give you a minute. We're looking at those first 4. And this is a VT plot, velocity versus time. I'm going to ask you guys about these 4 questions in about 1 minute. All right. So I'll wait till 2:25 on my clock on the screen there. When I ask you about these things, I'm also going to say, why did you think that? And it's okay to speak freely and honestly. All right. We want to discover what's in your brain and see if it's right or not. And if not, then I could say, oh, that's a good idea, but maybe think of it this way or something. I'll actually give you just a little bit extra while I sketch out this, just so I have it on the whiteboard for later. All right. And so let's take a look here. So again, I can't see it all. So anybody who wants to chime in, and we'll just try and mix it up and keep people alert. All right. So let's take this first question here. When is the object speeding up? Any thoughts, or is it?
It's not.
Okay. And what makes you think that? Just kind of, if you could give me some thought process, just so I have an idea.
At some point on the graph, you don't see any sort of upward movement.
Okay. So yeah, that's a good thought. It turns out that's not right. Shocking, right? So, all right. Good guess. So, is there anybody that thought it was speeding up? And if so, maybe you could speak up and explain your rationale. And if not, I'll explain it.
Is it speeding up because velocity is greater than 0?
No, that's not a true statement. So, good thought though. Velocity greater than 0 means moving forwards, but that doesn't necessarily mean speeding up. And that kind of alludes to maybe, all right. So maybe take another stab at it. Any other thoughts? There is one region of time or one time interval where it's speeding up.
So what I was thinking is that two things came to mind. I was like, speeding up, is it referring to acceleration?
Nope.
And
Oh,
yeah,
well, yeah, I guess so, right? Speed is related to velocity, but speeding up is related to acceleration. You're right.
Okay, so the only points where there is an acceleration, I would say after 3 seconds. So right there, there's an acceleration.
And where's the other acceleration?
So right there at 2 seconds, there's also, so there's a derivative both at those points.
Okay, now he said derivative, and since this is the calc-free class, what would be the graphical equivalent of derivative?
There's a slope.
Yeah, slope. So slope, if you have a slope, there's acceleration. Now we should be careful. What type of plot are we dealing with? VT. So remember that A is slope of VT, right? That's one of our bullets that we have on our chart. Okay, how do you know if something's speeding up or not? Why does acceleration matter? I'm just writing speeding up.
A change in height.
It relates to that, yeah. So if you have a change in height on this graph, and so I'm going to try and say a change in velocity because the height of this graph is velocity, right? And I just want to be careful when you say change in height. I think I know what you meant. You mean the height of the curve of the graph, but we want to be careful in the physics class because height usually is used in physics problems at the same time as velocity. So it's like, so you know what I'm saying?
Yeah.
And so I knew what you meant, but try to avoid that phrasing maybe. So speeding up, what does that say? If something's speeding up, what does that say about the signs of acceleration and velocity? Do you remember?
So if they're the same, you're going faster, and if they're opposite, you're slowing down.
So I want you to start thinking like this. Speeding up, I want your brain to immediately think A and V have same sign. Okay. So now help me out here. Let me do this. What's the sign of velocity right here for this green section I'm kind of sketching in?
It's positive.
Yeah, so here V is greater than 0. Do you agree even right here, V is greater than 0?
Yes.
Yeah, and so now what's the acceleration right here in this time interval, like right here, the first seconds?
It's constant.
Yeah, it's what constant?
So 0.
0. So the velocity is constant, which means acceleration 0. Do you agree this is A equals 0 as well?
Yes.
So how about right here? What's the acceleration right there? Is it positive or negative?
It's negative.
Yeah. A is less than 0. So based on that, does that fit the speeding up criteria? No. Velocity is positive sign. Acceleration is negative, right? So this means, yeah, let's see what the chat is. Okay. So now the next part is, how about over here? In this region, what's true about the velocity? Is the velocity positive or negative over here?
Negative.
Negative.
Negative. What about the acceleration?
Negative.
So is it speeding up?
Yes, but
Yeah,
negatively.
exactly.
Yes.
And maybe this would help. I was glossing over this point, but now you can see this. At this point, the velocity is equal to negative 2 meters per second I hat. But the speed is the absolute value of that, 2 meters per second, right? How about this purple point down here? There, the velocity is a larger negative number, negative 6 meters per second, I hat. But what's the speed? 6. Is it speeding up? You bet. Does that make a little bit more sense there? It's speeding. Yeah, it's okay. So it's speeding up from 3 to 6 seconds. Now, watch out, people. 3 to 6 is not correct. Units matter. 3 to 6 seconds would be correct. And to be honest, in Canvas, that probably won't come up. But on your final exam, if you don't put units on stuff, even if it's one of these simple questions, I will start dinging your score. And it's just a little bit, right? But I'm telling you that missing the units and stuff like that can add up to a letter grade eventually. So you really got to get in that habit of, when you read my solutions, make sure you actually check your own work. Did you write units like you're supposed to? Did I say something about it? If you didn't write units and my answer has units, you're going to lose points every single time, and it adds up. Okay. So be aware of that. Some of you in math classes are like, hey, should we use the square brackets or the round brackets? Blah, 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 blah. So let's say you did something like these intervals versus this. If you don't know what I'm talking about, it turns out I don't care. I don't care if you use open brackets, closed brackets, but I do care that this doesn't have the units. That would offend me. So you can put the units outside or something like that. So I don't care about open intervals and closed intervals. Yes, strictly speaking, it probably matters. Yeah. Okay. So there you go. All right. So cool enough on that. That was part A. When is the object speeding up? So that was the tricky one. Any questions before I erase this blob, or if you want me to erase it, I can do it again, or it's not speeding up at all from 1 to 2 seconds. And in fact, let's look. I'm going to clear this out right now. We can always put it back, or remember, you could always watch the live stream later. All right. I'm going to zoom in a little bit just so I can see better. So I want to zoom in on the graph. The next question is, when is it slowing down? Do you see that? Oh, that arrow is going to be on there. Hold on. I got to clear that. Let me make this bigger. Oh, geez. Zoom. All right. I guess I better make this 250. Oh, no. 200 is good enough. There we go. So now I have the whole graph on the screen. And so we're now looking. We know it's speeding up down here. This was the speed up. All right. And you could probably tell it's at rest right here. Do you agree? This point takes a minute for the zoom lag. There it's at rest. You could also say that's traveling with constant speed. I could care less. You could say it's traveling at 0 speed, right? And that technically fits a physics question, so that's okay. Where is it slowing down?
1.95 to 2.
Yep, this little spot right there. Excellent. What about this last chunk over here that I'm going to draw in light blue? What's that?
Constant speed
Yep, constant
at
speed.
4.
Yep, yep. All right, and so the you could see that first one was the trickiest one, right? So now in this case, we've got all right, so we kind of have a conceptual view of what this thing is doing. Great. Let's see if we answered everything. And let me bring this back down to 125. Oops. All right. So let's see. We kind of talked about this, and this. I think we've discussed that. So now I want to go over this stuff right here. I want to talk about the displacement on each interval and the acceleration over each interval. And so notice I basically split it up into 1 second increments with the exception of that weird little slopey thing from 1.95. Everything else. So again, we're going to talk about this, and I've got it drawn up on my board. I want to get the displacement and acceleration. All right, and so here it is. What do you think? Any ideas how to attack this? Let's start with the very beginning. It said we want displacement delta x in meters over these different time intervals. So the first one was 0 to 1. All right, and so any ideas how you get the displacement?
Well, we have velocity and time, so it's just t equals vt. So
Yeah.
4 times 1.
In terms of, yes, you're absolutely right. How does that relate to the graph? Is it a slope or an area?
An area.
Yes, absolutely. Do you see? He just said, isn't that just distance equals rate times time? You bet. That's this red area right here. This time interval is 1 second long. Apologies if that's too small. It's just limited whiteboard space. It's 1 second long. It's 4 meters per second tall. Right? So then it would be just the area. 4 meters per second times 1 second equals 4 meters. Now, because I wrote the units up here, I'm not going to write the units. Every time we're going to get meters per second times seconds, which is going to cancel out. And so we'll get just meters. And so to make this look a little prettier, what I'll do is I'll just write the number 4 here, and the units are included right there. All right. And then the next section, I guess you could probably, let me give myself a little bit of room here. So let me just show you what I did there. I did 1 second times 4 meters per second equals 4. And I'm not going to write the units on the last one just because I got it there. The next one would be how much time? Well, it would be this amount of time, right? Let me get a different color marker. It's hot out. That amount of time is 0.95 seconds, right? And so you'd have a 0.95 seconds times 4 meters per second, which should equal 3.8 meters up here. So far, so good? So I'll shade that one kind of lightly purple. This one is really hard to see in here. So maybe I'll blow that up. I'm going to exaggerate the triangle a little bit. The length of this triangle is 0.05 seconds. The height of it's 4 meters per second. So the area ends up being 1/2 base times height. So that's 2. You end up getting that's going to be 0.1. Well, let's write it. meters. So far, so good on these. I have no idea if this is working for you. And so if you're really good at this stuff, I already told you what problems you could work on. So if you feel I'm slowing you down, you've got the workbook, and that's the reason I wrote it, because not everybody's coming at this. Some people, this is the first time they've done this. If you've done this many times and you think you're good at it, it doesn't offend me if you just start working ahead and kind of tune me out. That said, why don't you at least stick around for the next step? Let's say we go from 2 to 3 here, all right? If we go from 2 to 3, oh, actually, that's easy. 0. There's no area, right? So how about from 3 to 4? What's that area going to be?
-1.
And that's what I was really hoping. I was trying to lull you guys to sleep to see if you would remember the minus sign, and you did. Great. Nice job. I was trying to sneak one past you, but I couldn't do it. So it's 1/2 times 1 second times -2, which is, I think, what'd you say? -1? Yeah. And then from 4 to 5, there's lots of ways you could do this. Any thoughts? I'm running out of colors here. Maybe I could use black.
I would probably do the area of the bigger triangle minus the area of the smaller triangle.
Oh, well, remember, we're only going from right here to right here. Oh, I see. Like that. Oh,
Yeah, so
interesting.
that big giant triangle, and then minus the area of the other
So
triangle.
he's saying take this entire triangle minus that one. That's a good way to do it. What's another way? Anybody else? Trying to get that black shaded area. That was a good way. You could Google the formula for a trapezoid, right? You could split it up into a small triangle that you've already done, plus a rectangle, which is what I'm going to do. I could tell this rectangle's got size 2. You could also do this. Think about this. If you took this little squirrely section, doesn't it exactly fill this squirrely section in here? So you could just say, I'll take the average height and just make it a rectangle. That's what the trapezoid formula is. So is there a recommended way? No. Any way that makes sense to you that gets the job done and gets this class over with is the right way. You know what I'm saying? So there's just some thought, because trapezoids are a little bit sneaky. You might find a trick. And then Esteban's is another one. Take the big triangle minus the little triangle. Cool. Anything goes. I don't care. Get the job done. That said, it's easiest for me to say, well, I know that size is 1. I know that's 2. So then I'll just write down the answer as -3. That's just the fastest for me. And then 5 to 6 would be what? -5, right? Because you just add another block of 2. Here's 2, 4, 5. All right. And maybe I'll shade this in lightly just so it's color-coded. Okay. So, yeah, I ran out of colors there. But the idea is this gets you the displacement. Now, be careful. Displacement and position are not the same thing. More on that later. The next part was asking us to get the acceleration in meters per second squared. Any ideas how we go about that?
For the time seconds they're asking for? Is it
Yeah. Each time interval, yep. Over each time interval, how would I get the acceleration?
So you're looking for the slope.
Slope. Excellent. So let's do the easy ones first. There's a lot of these regions that have the same slope, and a lot of these regions have 0, right? So let's get the zeros. That's always the easy points. So what time intervals have acceleration equal to 0? There, right? No slope. No slope. Right here from 2 to 3 is also no slope. And then right here, I don't know if you could tell, you go over 1 and down 2. Remember, this was negative. To be clear, I didn't label this axis. Sorry, this was -2, -4, -6. You have it labeled in your work. But so if it goes over 1 and down 2, I could tell these are all -2s. Right? Same slope. Then there's only one tricky region right here. Well, it goes, the slope right here would be -4 meters per second divided by 0.05 seconds. What are the units? Meters per second squared. So that, I think, turns out to be -80, doesn't it? That's 1/20th. So yeah, -80. Again, the only reason you don't see units here is because I did label them with units right there. And I don't know if I went too fast for you there, but so far, is that making any sense?
Yeah.
Okay. And now I need to go back to the screen share just to, there's a bunch of little tricks in here. Oh, there's a chat question here. Okay. And remember, at any time, you could ask Memo any questions you want. He's right there. So let's go check that screen share. And you can text each other if you want to. Let's do these solutions here. Oh, whoops. All right, and so here we are. That's basically the information. Here's that big table that we just worked out. I do want to point out a couple of things. In this case, the units are in the column heading, so it's not like I forgot the units. All right. Notice this. There's a subtle difference between the table of displacements versus positions, and this came up earlier. This up here is delta x. This is x. Why does x start at -4? What the? Why is it there?
Because that's where they started it.
How did you know that? You're right.
Just because it says they started there.
Yep, because the problem said so. Perfect answer. You are told it starts right here to the left. That's the negative sign, and here is the 4. Got it? So that's why I know the initial position is -4. All right, let's go back and look at that again. Whoops. Okay, and so now, just to be clear, take a look at this number here. This was the initial position from the problem. Between 0 and 1 seconds, the change is 4. It changed by +4. Between 1 and 1.95, the change is almost 4. It's 3.8. So it changed. Now take a look. You can see where I'm going with this, I hope. The change is 0.1. So that's not the x value. That's the change in the x value. Yeah, and then from there, I think you could follow it all the rest of the way down. Okay. All right, and so so far, so good. Now let's take a look down here on the next page. That's what I wanted to show. I made these plots of motion. Now they're not perfect, but they're pretty close. All right. And so this was my attempt to make those plots, and I need to stick in a few more points and improve this top one. This one was what we started with. That you could see it started at -4 from, whoops. This was what that problem just said. We start at -4, and then remember, this number 4 tells you that slope, right? Over 1 up 4. Over 1, almost all the way, up almost 4. And like I said, there's a little bit of a defect here in the graph that I couldn't do perfectly. But so that slope is 4 all the way up. Now, this section, the next section, because it happened so quickly, doesn't have a significant effect on the graph up here. It's not perfect, but we saw that it basically doesn't change a significant amount. It moves forwards another 0.1, and then it's basically sitting still. So that's supposed to be rapidly changing to sitting still right to there. Now, again, I need to put in more points so this doesn't get that weird curve in the graph, but it's basically supposed to be sitting still right there. All right. Next, it starts going downwards like this. And notice here, the slope is about 1 or 2. So that's that average slope is the velocity. Over here, the slope gets a little bit bigger. And then finally, the slope gets really big down here. It's really steep. And so that's how these graphs are related. Hopefully that's making a little bit of a sense on the XT. Any questions about that right now? I'll pause and get a sip of water.
Shouldn't the displacement graph not be curved where the
Exactly. It should be perfectly flat. I didn't put enough points in there. Oh, go ahead.
I'm saying in the last part of it where the velocity is constant, where it has the velocity is
The velocity is not constant at that last part.
Oh wait, never mind. I'm getting confused with acceleration. Sorry.
Yep. Good. Okay, it sounds like you got that. Other questions? Good comments. I'm going to go ahead and look at that acceleration graph right now. Remember, you got the live stream too. All right. Well, I keep hitting the wrong buttons today. Well, class, I guess it's been one of those days. Somebody gave me this joke flask. I was waiting for just the right time. It seemed like it. All right. That'll keep, yeah. Hopefully they watch that and fire me, right? Then I don't have to grade anymore. All right. So let's see. All right. Going back to here. Let's go down to here. So this is the acceleration plot. And I think, whoops, oh gosh. Let's do this now. I think we said right here, this is the color we used before. And I think, Esteban, is that what you were talking about?
Yeah.
And so
it's straight line because there's no change. I was totally getting confused.
Yep. So here he was saying the slope equals -2. And I'll emphasize that's the VT slope. And notice, and I'm being lazy with units, even though I told you not to be. That's why that number's -2. Now, notice there's this weird artifact here. We're going to ignore that. And then, I don't know if you remember right here, we said it was -80, right? Well, -80, that would be like way down there, all the way into the ground. Okay, so that's -80. Sorry, I couldn't draw it all on one graph. Okay, and then the rest of the time, hopefully you agree, here A was 0, A is 0. Here A is 0, here A is 0. And so that's seeing how these graphs all kind of come together. Any questions about that graph? All right. Check this out. Let's do one little extra nugget. Now, right here, I'm trying to color in this area. That area, shouldn't that equal -80 meters per second squared times, what was the length of that time interval? I think it was 0.05 seconds. Is that right?
Yes.
Thank you. Okay. What number does that turn out to be? I'm going to punch it in. I got a feeling it's -4.
Yeah, because we already did that calculation.
Yep.
Backwards,
So
though.
exactly. So this turns out to be -4, but give me the units.
Meters per second.
Absolutely. That is what? What is that area?
Velocity.
No. Close.
Change in velocity.
Delta V. Do you agree? It's none of those velocities at that time. Take a look. Here it's 4. Here it's 0. Delta V equals -4. Does that make sense? The subtle difference there, Esteban?
Yeah.
Sneaky, right? And what the hell? I'll throw in an I hat. We've been doing all this without the I hats, but hopefully you agree that we're assuming that is there. It just saves us so much time not to write I hat all the time. Great job. Hey, now I'm going to try this. I expect it to fail miserably, but let's see what we can do here. So we started out at -4, right? And then the velocity initially was +4, I think. And then the acceleration initially was 0, right? So I'm going to play this, and I got to stop this at 1.9 seconds or so. Here we go. Right there. So this isn't going to be perfect. Now I have to set the acceleration to -80, right? All right. And now I'm going to set the acceleration to 0. Whoops. And the velocity was supposed to be 0 there, wasn't? Oh, you could see I screwed this up. But yeah, you get the idea. It's trying to show this. All right. I'll let you try and do that on your own because I could tell it's very hard to click this and stop it in time. So that's my bad. If I could somehow stop it fast enough, it would have worked. But that gives you an idea, and that's where these plots are coming from. Oh, let's just set this to 0, and we'll set this to 0. So we play it for a minute, and then now this acceleration was supposed to be -2. All right, and we'll run that. And so that's supposed to be a sort of simulation of this. There's a little bit of a screw up right here because it wasn't supposed to go negative. So that should have been just straight down. And that's why this is supposed to flatten out, but whatever. Let me get the chat question here. Yeah, and you could, but it's like, whatever. You get the idea. And I think hopefully that gives you, oh, let's finish this out. Oh, let's play it back. Oh my gosh, what did I do? It's waiting. I'm waiting on Zoom to do something. Can you guys still hear me?
Yeah.
Okay. I've got an endless circle of death here. I don't know what's going on.
Yeah, I think Java's just crashing because Java sucks.
Yeah. All right. Hey, there we go. We'll just go back and get out of that and see if it quits in an hour or two. All right. So that we did kind of slow and in depth. Hopefully that gives you somewhat of a feeling for the ways you can go wrong. Now, typical Jorstead here, what am I going to do? We just spent a lot of time on what type of plot? VT. So next, let's look at, how about XT, right? So flip the page, look at number 2.28. I'll try to screen share. I don't know if it's going to let me. Maybe I'll just get rid of that one. Let's see if that fixed it. Nope. Oh, there it is. All right. And so we were right here. Let's go to the next one. This one. Oops. So hopefully this will fit on the page if I do it right. Okay. We're at 2.28. It's a little bit different looking curve now. All right. So I'll try and get this drawn up. I'm going to give you guys a minute to look at this one. And Take your time and see if you could chat with each other, or you could send Memo a question if you think you've got it. Just kind of go through these and see what you can do. If you want, you could do part B last, because that actually requires plugging in some numbers. So maybe do last. All right. I'll give you a second to look at that while I get it drawn up. Maybe we'll go till 3:03:03. I don't have room. All right. Close. Ooh, let's go 3:03:33. Oh, that water's strong stuff. Excuse me. All right. So maybe somebody feeling brave. And I know it's been, I forget who's been speaking up, but it's been mainly two voices. So maybe those of you that have been speaking up, let's try and hold out a little bit and see if somebody else will chime in. And I can't see you right now, so I won't even know. So don't be shy. And nobody on the live stream will know either. So yeah, let's look at this first question. List time intervals Zyker is moving to the right. This is a tough one, so just take a guess. It's okay to be wrong. I'll help you. Anybody feeling brave?
The 1 to 3 and 5 to 6.
1. So from 1 to 3 and from 5 to 6. What's the reasoning? Do you have an idea why, or is it just that's what you think? I haven't even
From 1 to 3, you're going from negative 20 meters to 20 meters.
Yeah, he says, look, I'm going from negative 20 to positive 20. Great. That's awesome. And then how about, I guess here you're going from what, negative to 0?
Yeah.
And that's absolutely correct. Great. How does that relate to that list of crap? Do you know? So that was good. So you're off the hook, but look at this list of crap right here. Remember this crap? We've got an XT graph. What's another way you could tell from one of those bullets? That was excellent. Sorry. There we go. What do you think? Anybody can speak up now.
Concavity.
What was that? I couldn't hear you in my headphones.
Like the concavity of the of the graph.
What does concavity tell you on an XT graph?
Acceleration is positive or negative.
Okay, so is acceleration the same thing as moving?
No, but it can answer part of the question. And then
Not
help you figure
really.
out the next part.
Yeah, it's good for these parts, the speeding up and slowing down. So that has to do with acceleration. Moving, when you see the word moving, I want you to think of not acceleration, but not position, not distance, not displacement, not speed. What?
Velocity.
Velocity. So if you're moving to the right, right usually means a plus sign. So this is basically asking, when is velocity greater than 0? Well, how do you get velocity from an XT graph?
The slope.
So let's go back and see if those regions have positive slope. From right here, positive slope, right? Still positive, and notice everything he said earlier makes sense. Then you have a large region with negative slopes, then here the slope is positive again. So those are two different ways. You could literally say, look, the number is getting bigger. It must be moving to the right. It's going from a negative number to a positive number. It went to the right. Or you could say it's got a positive slope. Those are kind of the two ways you might think about it. Great. If I want to get the, oh, what the heck? Let's skip to part C here. When is Zycra moving left and slowing down? So just, I'm going to clear all those drawings. Oh, were there any questions about that? Sorry. All right, let's skip to part C and try that. I'm going to sit down for a sec. All right, anybody's feeling brave. You know, the more you speak, the more fun you have and the more you get it down. So moving left, what does that mean?
Velocity less than 0.
Slowing down in this case means?
Acceleration greater than 0.
Exactly. Or I'll say A and V, opposite sign, which he went ahead and said what it was, which tells me in this case, because V is less than 0, that says A is greater than 0. And then going back to what you were saying earlier, what is the acceleration on here?
Positive.
I mean,
Like
is it the
concave
slope or is, yeah.
Oh.
It's the concavity, I think he said. So what we're looking for is a region that's concave up, but what is this? What does the velocity less than 0 tell us? For an XT graph, that means areas, slopes, derivatives, what?
Means a slope, a negative slope.
Yep. So now we know what we're looking for. So notice these words are looking for a negative slope, concave up. Well, this is concave up, and this is concave up. So it's got to be in that subset. And now we're looking for a negative slope. Well, this is a negative slope, and this is a negative slope. So there we go. That's moving left and slowing down. So far, so good. I'll let you do parts D and E at home, but I do want to focus on this part B that we skipped over now. Oops. This is something I discovered is worth talking about with students. I want the velocity at t equals 4 seconds. All right. How do I get the velocity from an xt graph?
Slope at any point would be the instantaneous velocity.
Slope. Excellent. And so what we want to do is a lot of students, I don't know why, but students will come out here and pick these 2 points and do rise over run, probably because they're the easiest to read off the graph. But I just want to point out something, how terrible that is. That's not a very accurate depiction of the slope. Do you agree? So when students did that, I just marked them off and said, you know what, that's not good enough. So what I want, and so since I've learned to be a little bit more clear about what I expect when you do a slope. All right, so let me undo that one and undo this and undo that. I expect you to pick points close. Like if you had done this point, the red point to the blue point, you'd be almost spot on. And I'd be like, yeah, that looks great. Or what if you had done the green point to the blue point? That would be spot on. In general, if you can do it, you should go from the red point to the green point. So this would be a really accurate slope. In general, if you could pick a time just before and a time just after, you get the most accurate slope. Why is that? Because the time before is a little bit too slow. The time after is a little bit too fast. And when you average them over that time interval, you get it almost perfectly. So in practice, numerically, this is what we do in physics. We take a time interval just after and a time interval just before, and we average them, and you get that spot on. So, and that is all worked out for you in the workbook. So I'll leave that for you, but that is what you would do for this part right here, the slope. You would get this rise over this run. Are there other ways to do it that are pretty close to that? You bet. And so all you have to do is get within 10% of mine on a Canvas quiz for this type of question. All right. So sometimes I'll even jack up the error tolerance to 15 if I think the graph is hard to read. But I do expect you to be better than 20% off, which is what those other points do. Did that make any sense on how to get that velocity? Just checking for some feedback here.
Yeah, just take the slope, but a close slope.
Yep. Now, for fun, let's go into here. Oh, I just threw away my simulation. I was going to simulate it, but oh well, that's fine. We'll leave that there. So I'll let you pick up the rest of that one later. All right. So I guess I drew all that for nothing, huh? Yeah. Well, yeah, I guess what we could do from this is we could use this really quickly to sketch what we think the VT plot should look like, right?
It would be a negative cosine.
Probably. So let's take a look here. But let's not overthink it. Let's get it approximately right. Okay. And let's not worry about the numbers exactly. Let's be approximately right. Right here, the velocity is negative, right? So I'd expect to get a negative velocity. And then right here, what's the velocity?
0.
0. Then right here, what's the velocity? Negative or positive?
Positive.
And so we could see, I think Esteban is about right. Now it's back to 0. Whoops, back to 0. Back to negative. Back to 0. Back to positive. And so I'm just kind of sketching this out. So that would be the VT plot. And then you could take the slope of this to get the acceleration plot, and et cetera. You're off to the races. So hopefully that gives you a kind of a little bit of an idea of what this thing is looking like. Now, we're not going to be doing calculus, but the easier way is to know this function and just take a derivative of it. But in practice, we don't usually have that. Okay, so for example, what do you do in a real world situation? A lot of times you take a video of something and then you track its motion in the video, and you don't have a function. You just have a bunch of points that are approximately this shape. So what could you do at that time? You could make a trend line and try and fit it with a function, then take the derivative of that function, Or better yet, you could learn numerical derivative techniques, which we will learn later, which is kind of like what I was just saying. Take the difference at each point and just get the average velocity at each point using that difference method, the slope, the rise of a run. And so in practice, what do we really do? We usually get the slope of this at every point using a little computer program and then hit fill down. So, all right. So it turns out that this slope calculation is actually pretty practical in the real world too. It just may not look like it yet. All right, what's next here? Let's see what we got. We've got about 20 minutes left. Oh, let's check the chat there. Yeah, something like that. Okay. So I don't know what I said there, but did I say it wrong? If I did, my bad. Thanks. Yeah, derivative of sine is cosine. So what did I want to do next here? I want to look at some of these 229s. All right, so what we've done right now is we've done a lot of problems, kind of maybe touching the surface, doing some numbers that way. I want to really hammer down the concepts. My belief is if you get really good at the concepts, you'll apply the right rules. It does you no good to be really good at doing the math if you constantly don't do the concept right. You just grab the wrong tool, do a bunch of great math, and it's all wrong anyways. That does you nothing. So let's make sure you understand these concepts. And I made a bunch of questions that I think will be kind of fun as I could make it. You could do this problem later. You could redo those problems that we just did later. These problems are going to be kind of fun here. So in the first lecture, I did 2.29 in a quarter. I want to try maybe this time doing 2.29 and a half. And so you could see we're in at about the hour mark. So, and this is about the same as the earlier lecture. So if you want to go watch 2.29 and a quarter, go to about the 1 hour mark of the previous live stream and just scroll through to find it. All right. That said, let's try and do 2.29 and a half down here. Let me clear my drawings. So we're going to try and do this. And you can see this plot has got 4 different objects on it. Object 1, 2, 3, 4. And you can see there's 4 different curves here. And what we want to do is analyze these curves. Each curve has a different pattern. And just to make it pop a little bit, maybe what I'll do is I will go to here and just line that one out. So you can really see that straight line standing out. It's a little hard to see. So that object 1 is that light purple line, and the rest have dotted lines that you can kind of see. All right. So in this case, let's see how you do. I'm going to give you a minute to think. Oh, do you guys like that where I give you a minute to think and then quiz you? That's what I usually do in real class, but this is Zoom. I don't know.
Which questions are we looking at?
Just all of these.
All of them? Okay.
Yeah, and just see how far you can get. But do you guys like that? Would I give you a minute to try it before I start yakking at you? Or do you?
Yeah. Yes.
Yeah.
Okay. Yeah, just a second to kind of digest. All right. So let's take a look at 2.29 and a half. I'll give you a second. And anybody that wants, you could add in the chat anything you want and ask questions, or you could chat with Memo if you just want to go, I hate this guy, I can't take this class, blah, blah, blah. Whatever works. I'll give you about another minute. All right. 3, 2, 1, 2, 3 seems like a good time to me. So let's do it. So apologies if I didn't give you enough time, but at least you had a second to kind of digest it a bit. All right. Look what we have here. The first thing I'm going to do is identify the type of plot because I don't want to screw up that. I've got a VT plot. Next, I read the question here. Rank the initial speeds. What does that mean on this plot? Anybody?
Rank the far left side.
Yeah, we're looking at the initials right here. Now, am I ranking? Okay, so let's see. So for example, this one looks like, what is that? 7.5? And I'm going to leave off the units because it's going to take me all day. That light purple one is probably 5. Oh, that other one, that dash dot. We'll call that this one. That dash dot is also 5. And then what's the other one? Probably this dashed. That one looks like it's, what's that one's speed?
It's about -3.
Nope.
Okay.
Speed.
2.5.
I gotcha. You know what I'm saying?
Oh, yeah.
Right. I was just, and that's why I asked it, because you're like, yeah, you could tell the number. And so these increments are about 2.5. So remember, all we have to do is just read the value. If we were on an XT plot, we'd have to get the slopes and crap. But so that was just checking. So so it looks like the smallest is 2. And then the next one is a tie between the green and the purple. The green is 3. And what's the next one? And 1. And then finally, the fastest initially is the red one, which was that guy. 4. All right. Sweet. Next. So that takes care of that problem. I'm going to clean up this a bit. Next up, the next question here. Oh, and let's get rid of that and this. All right. So now we're up to which objects have non-zero constant acceleration? Which ones do you think? Somebody, anybody, I don't care.
2 and 3.
All of them except for 1.
Let's see. So we see there's a contradiction here. So
Sorry, yeah. Actually, the last one is not.
So object 1 is A equals 0, right? Is that right? Yeah, because it's constant slope. All right, and then 4, oh yeah, 4 doesn't have it either. This one does, and this one does. Now, one of them is positive and one of them is negative, but I don't think it asked about that. It just said non-zero and constant. All right, that's cool. Let's get this out of here now. Let's keep going. Which ones are not moving?
They're all moving.
Exactly. They're all moving. Obviously, at this split second and at this split second, these two stop. But this is not an XT plot. So, right, this is a VT plot. That's basically checking if you're paying attention to what type of plot. Which objects have acceleration equals 0? I think we already answered that. All right. Which objects reverse direction?
1. No, that's...
Not 1. Do you agree?
It's,
4.
it's,
Okay, somebody
I'll
said
pick 3.
4. Okay, let's look at 4. 4 here, look, the velocity is 7.5 and it's positive. So it's moving to the right. Here, the velocity is 10. It's still moving to the right. Then it slows down, but it's still 7.5. That was a good guess. This curve is actually always moving to the right. If it was an xt plot, you're right. That would represent reversing direction. But in this case, all that's saying is it was going to the right at 7, sped up a little bit, then you took your foot off the gas a little bit. So that would be like trying to pass somebody. You speed up for a little bit and then slow down, but you're always going forwards. That's a tricky one.
So it'd be 2 and 3, both of them reverse.
This one has positive velocity, then negative. This one has negative velocity, then positive. That's the key to reversing direction. The velocity has to change sign. So that one would be, yeah, whatever that is. What is that? 2? No. 2 and 3? Sneaky, isn't it? All right. And then final speeds. I'm going to let you do that later. Monotonically increasing just means the velocity is either constant or increasing. That's what that means. And said another way, that just means the acceleration is always positive or 0. Do you see any objects that are increasing speed, increasing velocity monotonically?
Object 2.
Yep, object 2. And do any of them have monotonically changing speed? Again, that's the speed just gets bigger or stays the same, but it never gets smaller. Do any of them have that?
Object 2 and 3. No, never mind, because those are changing velocity.
Yeah,
Object
okay.
1.
Yeah, object 1 would fit the bill. Do you agree? That's sneaky. Object 1 has acceleration equal to 0 all the time. So according to this definition, that would fit that. So it's monotonically increasing with rate 0. It's not a very interesting problem. So yeah. Now here, this is where the speed is trickier than the velocity. Look, the speed goes down and goes to 0. Then the speed goes up. Clearly that's not monotonically increasing speed. This one right here has monotonically increasing velocity, but not speed. The speed goes from something to 0 and then 0 back up. So here, velocity is monotonically increasing, but speed is not. Don't you love physics? All right.
Does that mean that object 1 satisfies G as well? Because it has a constant velocity the whole time?
Oh yeah, it does. Yeah. And I think what you'll see in the solutions is when I do, let's just go look at the solution really quick. And then we probably should get on to the next one here. We're going to run out of time. But you'll see a lot of times I'll even kind of debate this. Yeah. So blah, 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 blah. We already know. So this meets the requirements of the statement. So I'll say that. And then, okay, you see I have some extra words in here. Be careful. So make sure you go through those solutions very carefully. And you can see sometimes I try to tell you what the point was. So I think these are pretty good questions in the sense of, I'm really trying to tell you what's important, not just the answer. All right. So let's go back to here. And then just how would you get the displacements? Don't get it. Just tell me how you would get it on this plot.
Areas of the
areas. Would you need to include plus minus signs or not for displacements?
No.
Yes. So displacements, this would be a negative displacement and this would be a positive displacement because you'd have to include the plus minus signs on the area. This would be a positive area and this would be a negative area. Distance is the one where you just always get the positive. Does that make sense?
Yeah, I always mix those two up.
Yep. And that's why we're doing this, right? So yeah, totally expected to. All right. Now, we're going to run out of time on the next one, but I'm going to go ahead and start it and get us rolling. We've got 5 minutes. Whoops, So let's scroll down here. I think the last class I did that one. So maybe let's do this one, 2.29 and 15/16. All right. So I'm going to give you a second to look at that one. Let's go to 333. All right. And then I'll just talk about it for a couple of minutes. And then if you have to take off after that, just take off. But maybe we'll talk about it for a few minutes. And if we bleed into office hours, we do. I'm not always going to do so much screen share, just today with these plots. Oh, we got to go 333.33. That's a Yahtzee. All right, 333.33. I don't know why. I just like silly little numbers. It's just something fun. Okay. In this case, let's make sure we at least get this first one before people have to take off. So part A, if we're doing part A here with this angry red arrow, let's even make like a mean face. Arr. All right. I don't know what's gotten into me today, but yeah. Okay. I'm supposed to rank the initial speeds. What's the first thing I should do before I do that?
Get all the slopes,
Okay. How did you know to get slopes?
because the slope of a line on a position graph is going to be the speed.
Okay. Yeah. So I just want to point out that he thought about the type of graph. Do you agree? So he's thinking this is an XT graph, and that is implied in what you just said. So that's the first thing in my mind is, geez, make sure you get the right graph. And then he said speed. What did you say that would be?
The slope of the line on a position graph.
Okay. And so somebody else that's not quite right. Can you tell why it's not exactly right? And
Because
you
you're
could-
looking
Oh,
you're
go ahead.
looking for the absolute value of the slope.
Absolute value of the slope, which he probably was going to do, but I'm just busting your chops for the precise language just because it's a
Yeah,
physics class.
okay.
You know what I'm saying? Does that make sense?
Yeah, I can
And
see
so, yeah, good. Nice job, though. He had the right idea and knew exactly what to do, and he was probably going to get this question right. So my point being is that that slope is the velocity. If I take the absolute value of it, I get the speed. And that's what we were supposed to rank. So then that's pretty close to 0. I don't know. Those two look about the same to me. And okay, so there you go. Oh, there's some weird artifact in there. I don't know what oh, that's probably from my chat box or something. There we go. Okay. Yeah, I had something weird from Zoom in there. All right. And so notice the difference here. The final velocities, you're going to worry about the minus signs. The speeds, you got to do the absolute values. And then from here, that's cool. Let's skip down. We didn't do these things. So let's look at these. You can see I'm basically asking exactly the same questions, but the rules you have to apply change and the figures change. And so the procedure of these is huge. I can't give you a cheat sheet for this. You just have to know how to do the procedures, read the graph, identify the type of graph, identify the correct set of rules, and then apply those rules correctly, being super, super picky about, did I say speed or velocity, distance or displacement, blah, 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 blah. All right. And that only comes with practice. You cannot get this right without practice. That said, let's take a look at these displacements. How would I get the displacements?
You got to take the slope to get the velocities, and then you can multiply
Nope.
by time.
You could do
So
that. That would be difficult though.
You just do final position minus initial
Exactly.
position.
So for this one, all I got to do is I get those 2 points, and it's going to be X final minus X initial. So you don't have to work that hard. Isn't that cool? That's a lot faster. And now what you were saying would have worked, but notice the velocity or the slope keeps changing. That would be extremely difficult. So, and so what we see here is displacement on a VT graph. You got to do a bunch of areas. It's hard. Displacement on an XT graph is like the easiest one. And so that just comes from practice. So let me do this. There we go. And so you could do the same thing for some of these other points. You could say this point and this point, and it gets a little bit messy here, but that's that. All right. So next, what if I wanted to do this question, rank the distance traveled? And we'll make this our last one. Again, if you have to take off, I'm not offended at all. You'll have this in the live stream if you want to catch up later. So if you got to leave, leave. That said, how do I get the distance traveled?
I would do meters on the right plus meters on the left. So everything on the.
How about this, Esteban? Just tell me one object. Let's start with one object. So pick one of them that's tricky and explain it.
Well, we'll go with the one with that has red on it already.
So that's object 14. Got it.
So you start at 5, and then you go wherever till 0 is till it hits the.
So right here.
No, sorry, it would be.
Okay.
That would be to the top of that curve.
Yes.
So right there, that's to the right.
So that maybe looks like, I don't know, I'm just kind of guessing. If this is 10 and that's 15, that's 12 and a half. So let's say that's 13. Are you okay with that?
Yeah.
And then you come all the way down to right here, which is basically negative 20. So let's actually, and I'm leaving off the units. This starts out at 5. So based off that, Esteban, give me the distance and explain how you're getting it.
So it would be 13 minus 5, which is 8. And then you have, what's
so that
the bottom?
Went 8 up. And are you okay if I put the meters only on the last part of it?
Okay.
Yep. So it went 8 up.
And then you would go negative 20 minus 13, which is negative 33.
Do you agree that's the same thing as 33
Absolutely, because you're
down, right?
Yes, yes.
So what's the total distance?
So then you'll be at 41.
Yeah, and what's the displacement?
The displacement is only, so you start at 5 and you went down to negative 20. So negative 20 minus 5 is negative 25.
So the displacement would equal negative 25. And once again, we see that if an object reverses direction, distance is not equal to displacement. And I'm going to underline T for distance and P for displacement. And that was great job. And just notice here, the velocity is greater than 0. It's moving forwards. Here, the velocity is less than 0. The slope is less than 0. It's moving backwards. That means here is where it reverses direction, right? That is where it reverses direction. All right. So I'm probably going to stop the live share there unless you guys have any questions before I erase it. That's sneaky. Great job today. Toughing it out. That was a tough day. All right. Whew.
All right. Well, thank you.
Yep. Good job. And thanks for